Hello everyone, welcome to section 5.3 on enthalpy. This is a very important and very long section, so we're going to break this up into several videos to break it down a little bit. So we'll do just a few of the learning objectives here in this video. The first one is state the first law of thermodynamics. The second one is define enthalpy and explain its classification as a state function. So let's go ahead and get started. This is actually one area of your textbook that I think could have been a little bit better organized, in that a lot of these ideas in the start of section 5.3 would have been helpful to cover prior to section 5.2. So we'll be, as we go through this, we might be referring back to section 5.2 and say, this is why we did it in that way back then. So we can think of thermochemistry as a subset of another area called thermodynamics, or specifically chemical thermodynamics. And thermodynamics is about energy and how energy is moving as we have various chemical processes going on. The two ways in which that can happen are heat and work. And we talked about those a little bit in the previous section, but we provide a lot more context to that in this section. So when we look at the ways in which matter is interacting and with energy, we can talk about matter as having something called the internal energy. Your book is using the letter U for internal energy. Sometimes, though, it's the letter E is used. So internal energy is all of the things inside of an object that are giving it energy. So you could have some examples here are shown. Kinetic energy based on the object moving, or parts of the object moving. If it's kind of the random motion we've talked about earlier, the molecules and atoms can vibrate and rotate. And there's lots of things here. We don't actually know all of the ways in which energy is contained within an object. What we do know is the ways that energy changes as it goes from one system to another, and we can talk about that. But this idea of internal energy is a little bit it's kind of like asking how deep the ocean is, right? We know now how deep it is, but at one point maybe we didn't. And so the idea of internal energy, we don't know how deep that goes. We do know ways in which energy does transfer between things. And there's actually only two ways that happens, heat and work. So this is a very important equation to understand in that context. The change in internal energy, again, we use this triangle symbol is the Greek letter delta, and we use that to represent a change. So the change in internal energy is because of either heat or work. So something can transfer energy by transferring heat or by doing work. So any change is because of one of those two things. This is called the first law of thermodynamics, otherwise known as the conservation of energy. Now, you might remember we talked about that in a previous section. Again, unfortunately, your textbook doesn't organize it in that way. One thing I want to mention is that energy is always positive going into the system. So positive Q, so heat flowing in is positive. Positive W, work done on the system is positive. And then negative if the system is doing work, or negative if heat is flowing out of the system. Okay, so one of the important things in thermodynamics is what we call a sign convention, which is simply saying what does positive mean, what does negative mean. Okay, so always positive in, always negative out. Here we're showing a picture of how that might work. So we're showing the system is this green blob, and then we have heat or work going in, heat or work coming out. Those are the two ways in which the system can interact with the surroundings. So heat or work. And we spent a big chunk of, well, basically all of 5.2 was about the heat and calorimetry, how we measure that. We didn't talk about the work. So we'll be talking about the work now. But again, having that understanding ahead of time would have been helpful if your book had been organized in that way. So there's lots of work that can happen. There's one we're going to focus on in this class, and that's called expansion work, sometimes called pressure volume work. And this is what happens when the system is pushing on its surroundings to expand its volume, and it's related to the pressure of that system, especially in the gas phase. Probably the best example of where this would happen is when you drive your car. If you have an internal combustion engine, which most of us do, you have work being done by the gasoline as it burns that pushes the cylinders of your car, that does all of the work that ends up pushing your car down the road. So it is a very important aspect of work in terms of understanding it. And it's one we'll be applying to how we understand chemical reactions. So one thing we should kind of pause for a minute and discuss related to thermodynamics in general is what this equation means. So the change in internal energy is equal to the heat plus the work. We have, when we write this, we show the U as uppercase and the Q and W as lowercase, and there's a reason for that. Internal energy is what we call a state function, and a state function is different than what heat and work are. They're actually called path functions. A lot of the way we manipulate mathematically the equations that show up in thermodynamics is based on wanting to have things as state functions instead of having them as a path function. So this equation is really helpful because we want to have state functions. The other reason it's helpful is it's relating to path functions, which sometimes are easier to measure. Okay, so the best illustration that people have come up with for explaining this is thinking of elevation. So elevation is a state function. It doesn't matter how you get to a certain height, you're still at that height. So here we're showing an example of somebody climbing a mountain. They could do it sort of this way where they go up a really steep incline, or they could do it this way where they kind of lazily, well, not lazily, but you know, they kind of take switchbacks, and the path to get there is longer, but they get to the same point. So regardless of how you got there, you're at the same point when you get to the top. You have the same elevation. So that's a state function. The path, how you got there, is different. You have different length in terms of the actual number of steps you took one way versus the other way. When we talk about the conservation of energy, we're talking about a state function. You could be potentially doing a lot of work and not having a big change, or likewise having a lot of heat flow, not having a big change, because those are not state functions. But when you put them together like this, they are. Okay, we're not going to go into a lot of depth on this, but it's just important to understand in terms of why we're doing what comes next, which is introducing this thing called enthalpy. Enthalpy is a very convenient way of talking about chemical changes, mainly because it is a state function that captures most of what we care about. So this is enthalpy. We don't actually use this equation because we don't actually know the internal energy. What we can measure is the changes. So the equation we're showing here is the useful one because we're showing it in terms of changes. So change in enthalpy is equal to change in internal energy plus the pressure times the change in volume. And so the key here is everything in this equation is a state function. And because of that, we can basically treat it sort of like the first law in terms of looking at changes. So this pressure times the change in volume is essentially the work that's being done by the expanding gas. And again, we're not going to get too deep into the derivation here, but what that equals out to is when you do the math here is the heat transfer at constant pressure. So this Q with a subscript of P, it means that the heat that is transferred at constant pressure. So why does this matter? The reason this matters is because we are able to use this definition to make a state function equal to a path function. And the path function we have here is one that we can easily measure. So we can measure the heat transfer at constant pressure. We actually already talked about how to do that in section 5.2. That is what the calorimeter is doing. When it's open to the air above it, you have a constant pressure. And so with that constant pressure, you have basically heat transfer at constant pressure equal to the change in enthalpy. When you have the bomb calorimeter, it doesn't work. So there's a different equation you would be using there. So this is very useful because we can make measurements, translate those measurements into changes in enthalpy, which is a state function. So that is kind of the idea of enthalpy. I think that we will stop there for that introduction, and then we'll start looking at how we apply it in the next video.